Hello class, and welcome to your lecture on networks and network analysis within primarily ArcGIS, but also the concepts transcend ArcGIS into any program that does networks and network analysis. All right, first and foremost, like with everyone, we're going to describe our terms and come to a common understanding of what is a network. A network is defined as a system of paths traveled by an agent. So let's go through some examples of agents and paths. So an agent might be a vehicle that travels along a path of roads, a network of roads. Agents can also be people moving over sidewalks, paths, roads as well. Water can be an agent, moving through a network of water pipes and streams. Electricity can also be an agent, working over a pathway of transmission lines. And we're going to talk about how those top two that operate off of roads, paths, and sidewalks are different than those that operate off of water pipes, streams, and transmission lines. So we have two primary types of GIS networks. The first is a utility network, or what's also called a directed network, also termed a geometric network. This is where an agent, primarily water or some other type of utility, can also be electricity, flows by a defined rules and predetermined paths, meaning that the agent doesn't get to decide where it goes on the paths. The path is set up to move the agent in specific directions at specific times. There is a predetermined source and sink in these networks. The source is where the agent would come from, and the sink is where that agent is moving towards. So the direction within these types of networks is always from the source toward the sink. So these types of networks are built when we're trying to model the flow of water, sewers, public utilities, and also electricity. And this also plays out with when we're modeling stream networks, because obviously in most places water is going to flow from a higher elevation to a lower elevation, and water's not going to start to flow backwards. So in those systems we always operate off of a source and sink model as well. So those networks would be directed or geometric networks. Some questions you can ask with utility networks are, if a water valve fails somewhere in the system, which customers would be affected? Because you can trace downstream of that particular valve and see who along the line would be affected. If a pipe is closed for repairs, where can water be rerouted to minimize service disruption? Because you can go up to the next place where there's a junction, and then you can see if you can route water around that. One that's kind of leans towards homeland security is if there's a contamination at one particular point, how would it spread throughout the system? And once it has started to spread, where could you go shut off valves in order to stop the spread? And another common question is that if you're flushing hydrants in a system, who's going to experience reduced water pressure, right? Because that's going to be everyone below that particular hydrant in your water system. So you always know where people are in relation to the flow of services. The other type of GIS network, and this is the type of network that we're going to play with in class, are called undirected networks, which are also transportation networks. This is where an agent can choose how they move on the network in any direction, but you can also build in rules for individual node locations and individual network paths about how that agent should be moving. So while in general you have undirected movement where the agent can choose wherever they want to go, we're going to talk about how you take a line data set, allow it to be this undirected network, and then also build a set of rules and restrictions that allow for the network to move agents along its paths that follow the real world rules. So some examples would be some one-way streets, not allowing U-turns, places where roads look to cross, but maybe you can't move from one road to another, like at an overpass. So those are the types of things we're going to talk through. So some questions that can be answered by these transportation networks are the things you do every day with your phone. What's the best path to travel, maybe to 10 different delivery locations? So one limitation of the free services out there on the internet, like through Google and Apple Maps, is that it's typically you can get from one source to one destination, right? One starting point to one end point. With the GIS tools, you can do multiple stopping points and find your best path between all of those. But transportation networks aren't just for traveling directions and for best travel routes. You can also build what we call service areas. So you can look around a location and see how long it takes on the street network for customers or individuals to get to you or to get away from you by driving along the network. So you can find best paths, shortest paths. We're going to talk about other things that are called location allocation, also origin destination cost matrices. It's all about that network and how those agents can move along the paths and the rules that you set up for that really drives the different types of questions that you can ask. So while you can't put in multiple locations into a lot of these free services, this is the type of thing, and these are the types of networks that all of your onboard GPS units in your cars, your GPS on your phone, when it's attached to a travel app, they are all tying into a vendor-provided transportation network that has a set of rules and a set of rules basically built in as to how the agents can move along the network. So let's talk about the specific network elements that help you to model this movement. So we're going to talk about edges, junctions, and turntables. These are the three primary network elements in any network. So an edge is what we would call a line. So as soon as you take a road data set and you convert it into a network data set, the network data set calls these lines edges, and agents move along edges in your network. Junctions are any place our edges or our road lines intersect. Think of those as our overlapping endpoints. So hopefully right now you're starting to think, this might be built off of topology, and that's very correct. You cannot build a network without having topology in your data set, without it following the rules of topology, meaning that where all features intersect, they are going to break. Now you can build a network so that you can model for overpasses, but you're still going to have the break at that overlap. We're going to talk about how we use elevation to model that overpass. But the way that these networks are built is that they adhere to topology rules of all features that overlap are going to break at that overlap, meaning that you're going to have coincident endpoints every time a line crosses. Those coincident endpoints are turned into what's called junctions in your network. And that is going to be where an agent gets the choice to move in a single direction or to change their direction along the network. And that leads us into turntables. Turntables are the things that are built into the network that are going to tell us what the cost is for moving from one network edge to another. So at each junction, there's going to be a table that's built that tells us the time, the cost that it takes to turn, to keep going straight, or to perhaps turn to the right or turn to the left. So if you look down here at this example, if this is junction ID 10, moving from edge 1 to edge 2 has a turn cost of 30. If we're moving from edge 1 to edge 3, we have a turn cost of 60. So this plays into these logical rules of how we travel along our networks in the United States. So this is specific to a system that travels on the right-hand side of the road. It is, in general, faster to turn right than it is to turn left because you're turning into the flow of traffic as opposed to crossing over traffic and having to merge in. So this is one of those basic concepts of any network, is that you're going to see that a lot of travel routes that are best and fastest routes have a lot of right-hand turns because you can do those faster than moving across a network to do a left-hand turn. So these turntables are actually built by the software. You can build your own, and there is copious documentation on how to build your own turntables. We'll talk about this a little bit in a second, and we'll talk about why we're not doing it. All right, so let's talk a little bit more about each of these features. So the edges are those Elements that connect to other elements at junctions, so there are lines. They represent the path of the network, and they come from a line feature class. So if you're modeling the flow of traffic, you're going to have roads as your lines that become edges. If you're modeling how people move across the landscape, you're going to use sidewalks as the pathway and as the lineway. If you're perhaps modeling how people use trails in a trail system and how they move along those trails or those pathways would be the line data set that you put into your network. So it's all about who your agent is and what type of path they move along, and that defines the type of edge that's going to be in your network. All right, so network junctions. These are the elements, so those points that connect our edges and facilitate flow. So junctions come from two sources, and this is what we're going to focus on. It is automatically constructed when a network is built. So as soon as you take a line data set and you run the network dataset construction tool on it, one of the things that gets created is that these junctions are created every time it sees an overlapping endpoint of lines. And that's what we're going to focus on. You can put in and load in specific junctions into a network. That most often gets done with those geometric networks, those directed networks where there are specific valve locations that move water along the system and also can stop water, even if there's not a choice of moving water onto another line, but they can stop it where it is. So a lot of people who build these those directed networks for utilities have a data set of point valves that they then load into their network to act as their junctions. And you can see here how they connect up your edges. All right, so coming back to our turntables. So this is how we move from one edge to another across our system. And it's going to record the amount of time it takes for your agent to go through the junction to each edge. So I mentioned that we can build these turntables. It's a rather time-intensive effort to do so. I did years ago have a friend who worked for Deerfield Township. She was the GIS manager for Deerfield Township here in Southwest Ohio. And they were working on a project where they were looking to find what would be the best new location for a firehouse in Deerfield Township. And one way they were doing that is they were trying to figure out what the travel times were for fire trucks along all of the roads within Deerfield Township. So she spent a summer writing the fire trucks in Deerfield Township with a GPS unit and a stopwatch. And at every intersection, she would take a GPS point and she would then time the amount of time that it took the fire truck to make each turn at each intersection. And she used that field data to build a very detailed turntable that was specific to the travel times and the turn times for their fire trucks in Deerfield Township. And it really helped them to better model how fire trucks moved throughout their township. And also it helped them identify a better location for where fire trucks could be placed, because in the United States, fire response has a set of federal rules that they have to adhere to. They have to get to all of their calls within a set time of 2, 4, 6, and 8 minutes. So every year, firehouses and municipalities and counties in the United States have federal reporting requirements where they have to say the percentage of runs that they that they were able to get to within 2, 4, 6, and 8 minutes. So it's important when you're placing a new firehouse in a growing community that you place it so that you can get to the constituents in your area within that defined amount of time. Now, I will say that when you're building your own network, you would have to build these particular turntables or find the turntable from a friend. Like for one point in time, I borrowed her turntable and just assumed that the travel times across certain types of edges would be similar for us than it was for Deerfield Township. Two very similar areas, kind of rural with a mix of urban. When we use a vendor-provided network data set, which like we're going to do for most of our activities for this module, these types of turntables are built into the system. So one thing you get when you use a vendor-provided network is you get a lot of these detailed elements already built in, because that's what you're paying for. You're paying for them to already have done a lot of this behind the scenes work that's going to make your routing even more specific. So we will not be building our turntables, but we're going to be looking at them. We're going to be still investigating them and understanding how they are helping to better model how our agents move across our networks. All right, this is what a global turntable looks like. So when you're building your own network, and you have a resource in your reading that talks about how you would build a network off of just a roads data set, you would use the network analyst tools to build your network. You can tap into the global turntable. And the global turntable is not really global. It's more built, again, we're driving on the right-hand side of the road, so this is very right-hand side of the road driving specific for our global turntable with Esri. Is the idea that you break out your 4 different pathways, and then you can assign travel time to them. So this is just giving you this width in degrees. This isn't travel times. This is just about the width on the network of what defines turning right, what defines turning left, because not every intersection is a right angle, correct? Sometimes you have ones that go skewed off. So this is just saying that a right-hand turn would cover everything in this area. If you were traveling from this direction, it would turning into any of these. So this global turntable is a global turn delay evaluator. It's within these defined 4 quadrants. What is the delay in traveling into each of those? So that's what the global turntable is. And if you build your own network, more often than not, you just rely upon this, because it's basically modeling that right-hand turns go faster than left-hand turns. All right, so we're coming back to how does this all work, right? We've talked about this a little bit, is that it's relied upon the concept of overlapping endpoints, which is our connectivity topology. Coincidence. What is the coincident feature? It is our endpoints. So we must have data that is topologically correct in order to be able to model across our network, across our edges. So networks are built in environments that can develop and interpret topology. So in ArcGIS, your network is going to always live in a geodatabase feature data set. Now, the network we use is going to be provided by the vendor. So we're going to tap into a network that lives in the cloud. But you can build your own networks, and you have resources that walk you through that process. And when you do that, you would create your network data set inside of a geodatabase feature data set. The reason why it needs to be there is because that's where topology is able to be stored within the ArcGIS and Esri data model. So that's why your network data sets end up living within a geodatabase feature data set if you build them on your own. All right, so that's the background about those, what a network is, but what can you do with networks, specifically within the Esri software? You can do routing, you can create service areas, closest facilities, origin destination cost matrices, location allocation, and we're going to talk through each of these a little bit, and then you will have activities that focus on them as well. All right, so routing is that thing that you do all the time, getting from point A to point B. However, when you're using a tool like this, you typically have more than one location that you want to get to throughout a route. So the tools allow you to find the best routes based upon time, based upon distance. So those 2 concepts there are what we call impedance. So what is the cost? What is it that you're accumulating as you move across your network? Do you want to be impeded by distance, or do you want to be impeded by time? What is it that you want to minimize? And this is typically termed the traveling salesman problem. So given a set of delivery stops, what's the optimal route? Do you have to go in the defined order? So are you doing a delivery route that people know what time to expect you, so you can't reorder your stops? Or are you doing a delivery route that it doesn't matter what time you get to people? Maybe you're an Amazon deliverer, and it just matters that you get to them in a single day. So maybe if you've gotten a bunch of addresses, you could potentially reorder them to best match what you want to do for your day. Can you start from one location and come back to that location? Can you model a route that would take you in a circular route? Could you start at a defined place and then start at and end at a defined location, so that all of your route in between was modeling the best route between those 2? Yes, you can. In fact, years ago, I had a student who, after this module, she took her dad's delivery route. So he worked for Frito-Lay in Cincinnati, she took his delivery route, plugged it into the network analysis tools that we had, and she was able to cut off 2 to 3 hours from his delivery route every day. So this has really very practical applications in the real world as well. All right, so that's traveling along the network route. So let's talk about this concept of service areas. A service area is defined as a region that encompasses all accessible streets that are within a specified impedance. And remember, impedance can be either travel time or travel distance. So this is the same concept of buffers in that it's looking from a location and looking out a defined amount of something. But instead of a defined amount of distance, so that straight line distance for a buffer, your defined amount here is travel time or travel distance. So you can see over here on the image that what they were asked to solve here is for this yellow location, find all the roads that are within a 10-minute drive of this facility. So here's our facility, all right, and what roads would be encompassed within a 10-minute drive time of this facility. So you can see how the edge of the service area ends at roads. So you have a little bit, it's not smooth along the edges because it's going out along the road network to find travel time and travel distance. Also notice that we have different types of roads. So the majority of these roads here would be what we would call local roads. And maybe this right here would be a state highway. But we also have an interstate system that's built into this road network. And then remember that you can travel faster on interstates than you can on local roads. So that's why with a 10-minute drive time, you get these little pockets up here away from the facility, away from the general service area, but still connected. So this is where we start to ask, how many people live within the area of a particular facility? How many people or how much of your area is within 10 minutes of your movie theater, 1 mile of your grocery store? This is where you get to see kind of where your customer base is if you know that people are willing to travel a certain amount of time to get to you. It also helps to identify satellite areas that might not feel like they're part of your area, but they might be. So if this particular facility understands that people are willing to drive 10 minutes to get to them, they might think to do advertising in just this local little area, right? Some flyers or maybe some billboards along this interstate. But actually, if they were to do some marketing up here in this area or over here, they might actually get customers from these communities because they are within that shorter drive time based upon just hopping on the interstate and coming down here. So it helps you understand your landscape, the human-built landscape, a little bit more if travel time and travel distance means something to your business or to the question you're trying to ask. All right, so let's talk about the closest facility analysis within the network tools. This is going to find the closest locations, which are facilities, from sites, which are termed incidents, based on the impedance chosen. Again, remember, impedance is either distance or time and the amount of that. So some questions you can ask are, what is the closest hospital from an accident? So the accident would be the incident. The hospital would be the facility. So if you had a data set of hospitals and you knew the location of an accident, you could very quickly identify which hospital is closest based upon your network route. You could also, for a neighborhood, do the centroid of a neighborhood. And if you had geocoded points for grocery stores, your incident would be your neighborhood point. Your facilities would be the grocery stores, and you could find which grocery stores were closest. Another one here, and this is the graphic that you see on the right-hand side, if you had a school that wanted to go on a walking field trip and it had a couple of parks to choose from, what's the closest park for a field trip? So you would have your site, your incident, be your school. The facilities would be your parks, and so you would put in all of your parks, and it would identify the park, and it would also define the route. So the thing with closest facility analysis is that it not only finds the closest location, the closest facility from a group of facilities that you're looking at, but it also gives you a network route and also driving directions to get to that location. So we're going to talk about how origin destination cost matrices are similar to that, but different in the type of output that they give you. So origin destination cost matrices find and measure the least cost paths from multiple origins to single or multiple destinations. So it's similar to our closest facility analysis in that it's finding things that are closest to you, but it's not going to define driving directions for you because we're typically putting in lots of potential origins and potentially lots of destinations. So let's walk through some of the questions you can ask with this, and then we'll talk about the little graphic on the right. So questions you could ask for this are, how far are individual houses from firehouses, and which houses get allocated to which firehouses based upon travel time in a community? So we would input all of our houses as our origins and all of our firehouses or destinations, or you could even flip that. So one is an origin and one is a destination. And what it's going to do is it's going to go through and look at, by travel time, it's going to look at how far you are to each of these firehouses or how far you are to each of the individual houses. You could also have a single destination of a working location and have all of your employees geocoded, and then you could model how far do your employees travel back and forth to work every day. It's very similar if you were a business and you had all of your customers geocoded and you wanted to know the average drive time for all of your customers. You could have your business location be the destination, and then you could have your customers be the origins, and then you can figure out how far they travel across your road network to get to you each time they travel to you. Now, what I want you to look at on the right hand side here is how that output is different. I'm going to go back one slide from this output. The output from closest facility analysis is a single driving route between a single origin and a single destination. Our origin destination cost matrix is not driving routes. It is individual straight lines that connect an origin point to their destination. So think of this as connecting the customer to the store. That line is a GIS data set. However, the line doesn't mean anything for travel routing. You can't follow that line unless you're flying maybe in a plane. What that line holds with attributes is information on the travel distance along the network to get from your origin to your destination, and then also information perhaps about time if you've asked for time as well. So instead of generating hundreds and maybe even thousands of driving routes, which is really computer and time intensive and memory intensive on a computer, what it does is it follows for each of your origins. It follows the network to get to the destination. And then instead of saving that route as lines, it saves it as accumulated impedance, accumulated time and accumulated distance, and then attributes that line with those values. So you're going to have an activity that's going to walk you through that so that you can see how that plays out. All right, the last thing we're going to talk about is location allocation. There are a lot of things you can do with location allocation within the ArcGIS suite. So we're only going to talk about it in general, and then you'll have one activity that you have the option to do that's going to look at a specific location allocation that's going to be a market share analysis. But in general, location allocation is the process of finding the best locations for one or more facilities that will service a given set of points. It then assigns these points to the facility, so it allocates them to that, taking into account factors such as the number of facilities available, their cost, meaning how long does it take to get there, and their maximum impedance from a facility to a point. So on the right-hand side, you can see how they start to look like origin destination cost matrices, right? You're connecting up a set of points to a destination, but it's doing it with a different set of rules. It's not now it's not just about travel time to your destinations, but it's also about each of these destinations now has rules about the number it can accept and the maximum travel time outside of them. So notice that there are points in here that have not been allocated. That's because they're outside of that impedance or that potential travel time to that location. So one thing that communities use a location allocation analysis for is when it comes to duplicated emergency services. So over time, communities have changed, right? They've incorporated new areas. They've stood up new first responders. Communities now are also shifting. Populations are shifting from maybe the interior of the city to the suburbs. And actually now we're starting to see a reversal of that. So it may not be that our emergency services, our firehouses, our police stations, our ambulance bays, they may not be set up anymore for the best service of our community. So one way you can test for that is to run a location allocation and look at all of the individual housing locations in your community, look at all of the locations of your emergency service bays, and then do a location allocation analysis that looks at who in the community would be allocated to each of those responding centers based upon time, because remember there's federal requirements on time. So you could look at them based on the time and then in the maximum number of people that they should be servicing. And then you could start to see if you have any duplicate facilities. So maybe you're duplicating efforts in your firehouses, and you could close one and move it to a new location as opposed to keeping that one open and opening another one. So you could maybe keep the same number in your community, but just move the location. So that's a very classic conversation that a lot of communities are having right now. If you go to the world more of business and marketing, there's this classic example of Walgreens versus their competitors and CVS. So you could ask a question of basically any business that's a franchise, where should you put your next business? Because you have a knowledge of where your customers come from, how far they're willing to travel to get to you. So you have an understanding of demand within a community. So those are your potential customers. You also know where your existing facilities are. So if you're wanting to build a new one in the community, you might know that you already have a couple, so you'd know where those are. So you'd want to know where your other stores are. You'd also want to know where your competitors are and what kind of travel time maybe they would get from their customers. So that's that cost. How far are people willing to travel? So then if you do an analysis within location allocation, you could look at where are your customers being allocated to within the existing set of stores, within the existing set of Walgreens and all of their competitors. Where are people being allocated? And are there pockets of unallocated customers? And maybe you could place a new store in an area where people are outside of that maximum impedance, that maximum travel time to you. Or maybe one store has way too much demand, and you could put another one close by and they could share the demand of the area and it wouldn't hurt the business model in general. So those are the types of questions that you can answer with location allocation. All right, so now that we've talked through a lot of what you can do with networks, it's important to understand some key terms that you're going to see within any network data set, whether you're building it or you're using a vendor-provided one. The first is this concept of cost. Cost is the attribute that's used to model impedance. So this is an obstacle or something that limits movement. Cost is proportional along the edges, meaning that as you travel along a road, your cost is going to get smaller and smaller as you move towards your destination. So the two costs that model impedance within networks are either travel distance or travel time. Travel distance is modeled by the length of each road segment. So obviously as you travel across it, there's more behind you and there's less in front of you, so it's getting smaller as you go. Then there's travel time, and travel time is calculated for each road segment. It's based on a combination of the length of the road and the speed limit on that road. So travel time, it's not magic. They don't know exactly how the travel time of each road without these two pieces of information. They have to know the length of the road and the speed limit of the road. And that's how they're modeling travel time for each road segment. There are also this concept of restrictions, and this is anything that restricts movement across the network, anything that makes it so the agent can't make its own decisions as it goes. So a lot of times these restrictions are one-way streets. You can also have restrictions that you put in as barriers. So maybe a road gets closed, and obviously that's a restriction. Or maybe one particular turn you can't turn right during certain times of the day, and those types of rules would be built into the network as well. Then there's the concept of hierarchy. So this is an ordered grade for each network element, so for each network edge. So hierarchy is used to model the time spent at junctions when you move from one to another. So hierarchy really looks at your road types. So you have your higher hierarchies, which are your limited access interstates, and your lowest hierarchies, which are your local roads. So on that continuum, it knows that, so it's going to assign a hierarchy number to each type of road in the system. So here's where on your streets data set, if you're building it yourself, you need to know what type of road each of them are. And this is usually provided when whoever's giving you your roads, they have identified a type of road that each road is. And you take that type and you transfer that type into a hierarchy number. And when the network solver is working and it's using those global turntables, when you come to a junction, it knows that if you're moving from one road element to the next of the same hierarchy, that travel is usually takes less time to move from the same hierarchy. You're staying on the same road type. But it knows that in the United States, that if you're moving from one road type to another, let's say you're getting off onto a state highway from a local road, it knows that there's probably going to be a stop sign or a stop light there that's monitoring your traffic flow. You can't just automatically decide to merge onto that road. You have to come to a physical stop, and sometimes there's a light telling you when you can move. So that's going to take a longer time. So it's just about modeling that time that you spend at junctions moving from one hierarchy to another. And that's what helps us get more accurate timing in our travel time. All right, some important terms to understand with cost. So that travel distance, also miles, is the length of your field recalculated to miles. So if you need to do this on your own, you would simply add a field to your roads data set if it didn't already have a distance in miles. But you know that every line data set has a length field. That length is going to be in the units of your coordinate system. So if you needed miles in order to build a road network, you would add a field called miles. You would calculate the geometry of that particular field to be the length in miles. If there's no calculate geometry tool, you know that you could just set up an equation that would convert whatever your length units are into miles, and that gives you your miles field. For travel time, if you need to calculate this, like I mentioned, it's a function of the speed limit field, assuming that you have a speed limit field in your roads data set, used with miles, because you need to know the minutes that you spend on each road segment based upon the speed limit and the distance. So there's the equation to get to that. Your minutes of travel is equal to your miles field times 60 divided by your speed limit. So that's the equation that would get you minutes traveled on each line segment. All right, so for restrictions, the most common restriction is one way. And if you're building your own network, once again, you need to understand how to build that one-way field. Sometimes your network data, your roads data set will have a field called one-way. And you just need to understand the different ways that it's identifying travel direction along that particular road. And sometimes you might have to change it in order for a vendor provided, say Esri, network dataset wizard builder to understand the field. But if you're in ArcGIS and you're modeling one-way streets, this is from the help documentation in Esri. So it will recognize these following three things. It will recognize in a field of one-way, FT or F is indicating a one-way street permitting travel in the digitized direction of the edge. So that means from the from node to the to node. So here you have to know the digitized direction of your lines in order to properly model one-way traffic flow. So if it has an FT or an F, that means that the one-way on that street is allowing traffic to flow in the digitized direction of the edge. If you have a TF or a T, that means that you're only permitted to travel against the digitized direction. So you from the to node over to the from node, so kind of backwards along the digitized direction. And in those fields indicates that you can travel either direction. So a lot of times the streets data set is going to have some sort of field that indicates this movement of traffic when it comes to one-ways. Now, if you have a data set that and you won't need to do this for this class, but this is just FYI, good information to know when you go out into the real world. If you're ever building one of these networks and working with roads, and you find a road where the one-way information is wrong in the field, or it's actually maybe something's changed, like a street in your neighborhood or in your community has changed to be one way or has flipped in direction, which happens all the time. You can manage this a couple of different ways. You can either change the attributes in the field So if it's flipping in direction, you would just change it from an FT to a TF. Or if it's going from a bimodal transport, so you could go either direction to a single, you could change it from the N or whatever's there to FT or TF, whatever you need. Or you can also get in and change the geometry of the line. You can always flip the digitized direction of a line by selecting it and doing the editing tool of flip, which is going to flip your from and to nodes. Most often people deal with this by changing the attributes in the network, but just know that you could also change the geometry of the line, and then you wouldn't change the attributes because the line would flip, those endpoints would flip, meaning that your attributes would now be correct. All right, so that's information to know if you ever need to build your own network. The network that we're going to use for our activities already has this all built in, but I want you to understand how it knows what the one-way streets are because there is an attribute in the network data set that you're going to be accessing that indicates all of this information. All right, we've talked about this when we talked about hierarchy before. So here is just another screen showing you what this typical hierarchies are within a network data set. There are traditionally 3 hierarchies: primary, secondary, and local roads stored in a field called hierarchy within the network data set. This is something where you have to go in to your base data if you're creating your own network and identify what are primary, secondary, and local roads. You typically have to then add a hierarchy field and then select for all of your primary roads, give them a hierarchy value of 1, select for all your secondary, they would get a hierarchy value of 2, and select for all of your local roads and give them a hierarchy of 3. So it's that iterative select and then calculate value process when managing your GIS data. All right, so network analysis with our Esri programs and tools requires the network analyst extension. It is a separate extension. We have it at Miami, but just know that when you go to the outside world, not everyone has access to the network analyst extension. You also, for data, need a network that is built off of line data, typically roads, unless you're modeling sidewalks, and then maybe you've built your network off of sidewalks. With our Esri licensing, we have access to the Esri World Roads Network dataset, and that's what we're going to be using for our activities. You can also build your own local road network dataset. Communities do it all the time. You have resources about how to do that. And just know that ArcPro now has the ability to do this. It was 2.5 was the first time that ArcPro brought back the ability to build a network data set. We've been able to build network data sets with ArcMap for decades, but Pro took a little bit longer to put those tools into its tool set. So now you can use ArcPro to build your own network data set and do your own network modeling. All right, here's some additional resources for you. And after this, it's just going to be about getting on to some of your activities.